Welcome back to the Deep Dive. So if you're running a modern OS, especially Linux, you rely on this piece of software that, well, honestly, you probably only notice when it messes up.
Yeah, exactly. It's like the engine room of your whole system, isn't it? For any modern GNU Linux setup.
It really is the heart. It handles, everything from installing your browser to patching critical security holes.
And we're talking, of course, about the package manager. And look, for anyone working with Linux sysadmins, devs, even just curious learners, it pretty quickly boils down to two main players, two big families of tools that kind of define their whole ecosystems.
Right. So today we're really diving deep into the DNA of system management. We're pitting APT, that's the advanced packaging tool driving Debian, Ubuntu, all those guys against DNF.
DNF, yeah. Dandified YUM. That's the core of Fedora, Red Hat Enterprise Linux, CentOS, that whole RPM world.
So our mission today, what we want you to get out of this, is a real solid understanding. We'll look at where they came from.
That shared history.
Exactly. And how they're actually quite similar day to day makes switching easier.
Yep. But also, crucially, where they really differ under the hood, architecturally. Things like admin control, stability, that kind of stuff.
Okay, let's unpack that. Starting with the history. Because to really get why APT and DNF are so clever now, you have to remember the problem they solved.
Oh, yeah. The absolute nightmare that was dependency hell.
Right. It was awful. Before these smart tools, you just had the low-level stuff, the basic installers.
Yeah. On the Debian side, you had dpkg for the .deb files.
Yeah.
Over in the Red Hat world, you had RPM for .rpm files.
And these tools were, well, they were basically just delivery trucks, weren't they?
Pretty much. Good at dropping off one package file in the right directory.
But they had no map, zero concept of dependencies. If you tried to install, say, some old media player, and it needed 6 other libraries.
dpkg or RPM would just fail. They list the missing files, and then it was up to you.
Oh, I remember this.
Yeah, the poor user. Trying to hunt down those files only to find they needed other files. It just cascaded. Turned installing anything into this ridiculous puzzle.
I definitely wasted hours, maybe days, manually sorting out library conflicts back in the late 90s.
Yeah.
It's honestly why some people just gave up on Linux back then.
It really was a barrier. So, okay, how did the smart solutions fix this?
Let's start with Debian's side. How did APT come about?
So Debian's approach was more like additive refinement. In 1998, apt-get appeared, and that was the revolutionary bit. The smart front end.
Right.
Its job wasn't just installing one file. It used clever algorithms to read metadata, info about packages from servers, the repositories.
The map.
Exactly, the map. It figured out the whole dependency tree automatically, downloaded everything needed, and then sequenced it all, feeding the files nicely to dpkg to do the actual unpacking.
And that combo, apt-get for installing and apt-cache for searching, that was the standard for, what, over a decade?
Yeah, a long time. But users had to juggle these different commands. It wasn't super unified. That changed pretty significantly around 2014.
Right, when they introduced the single apt command.
Correct. The modern apt command we mostly use now, it just tidied everything up, unified the experience, gave us that nice progress bar. It was more about polish and consistency for that huge Debian Ubuntu ecosystem.
Okay, so evolution on the Debian side. Now, the Red Hat world, their path was a bit more bumpy. They started with YUM.
YUM, yeah. Yellow Dog Updater, modified. It did the job for years, solving the basic dependency problem. But it had some pretty serious issues, architectural problems, really. That's why DNF became necessary.
What kinds of problems?
Well, YUM got a reputation for being slow, really slow sometimes, and it used a lot of memory. Plus, its dependency solving, sometimes it just failed on really complex updates or installs.
Any idea why? Technically?
A big part of it was its heavy reliance on Python 2 back then, and the actual logic for resolving dependencies wasn't super optimized. It just didn't scale well as repositories got massive.
Okay, so when a core tool like that is slow and occasionally unreliable, yeah, you need a fresh start. That's DNF's cue.
Exactly. DNF, Dandified YUM, was a ground-up rewrite. Architecturally, totally different. They were smart, though. They kept it command-line compatible with YUM.
Crucial for sysadmins.
Totally. Made the transition much smoother. But inside, completely different beast. DNF was built around one really key component, the libsolve library.
Libsolve. We hear that name a lot. What actually makes it so special? Why is it state-of-the-art?
Performance and reliability, basically. It comes down to better engineering. YMM's old logic, mostly in Python, just wasn't fast enough for these complex calculations. Libsolve, though, is written in C. It's a dedicated library specifically designed for one job, solving dependencies ultra-fast.
How does it do that?
It treats the whole dependency list like a mathematical puzzle, a constraint satisfaction problem. It builds this graph of what needs what and solves it way, way faster and more reliably than YUM's older methods ever could.
Okay, so switching from like a general purpose scripting approach to a specialized compiled C library that explains the speed boost.
Massive difference. And that's why DNF could take over relatively quickly. It showed up in Fedora 18 back in 2013, and by 2019, it was the official default in RHEL 8, replacing YUM completely.
Right. So we've got these two tools, APT and DNF, born in different communities, different histories, but ultimately solving the same big problem, dependency hell, successfully.
Yeah, absolutely. Which brings us nicely to how they're actually quite similar in practice.
This is great news for anyone like me sometimes, who has to jump between, say, an Ubuntu server and a Fedora workstation. The day-to-day commands feel almost the same.
They really do. Their main purpose is identical. They hide the low-level dpkg or RPM stuff. You, the admin or user, just say what you want, install this package, and the manager figures out how to make it happen safely.
They're the smart frontends doing all that calculation.
Exactly. And they both rely entirely on those remote software repositories, right? They need that connection.
Can't work without them.
Nope. Both keep a list of servers configured. They pull down the metadata package names, versions, who depends on what, and then they grab the actual software files. If you don't update that local metadata list, your package manager is basically flying blind. It won't know about new security patches or software versions.
But a real win, for practical purposes, is how similar the commands are now. Give it the quick cheat sheet.
It's almost seamless for the common stuff. Installing.apt install nano on Debian Ubuntu, DNF install nano on Fedora HL.
Same command?
Pretty much. Searching.apt search Firefox versus DNF search Firefox. Removing.apt remove versus DNF remove. Even upgrading your whole system. Apt upgrade versus DNF upgrade. The muscle memory just transfers over. It's really convenient.
And they both share that critical idea of transaction stability. You mentioned they figure out the whole operation first. So if I'm installing, say, a web server and it pulls in 10 dependencies, but my internet flakes out halfway through downloading file number 9, what stops my system from being left half broken?
That's the transactional part. Both APT and DNF calculate the entire set of actions first. Download everything needed, verify the files, and only then do they actually commit the changes to your system.
Ah, so it's all or nothing.
Exactly, all or nothing. If anything goes wrong, network drop, disk full, dependency conflict discovered late, the whole operation gets aborted, rolled back automatically before it starts installing usually, nothing gets changed. It prevents leaving your system in some weird, inconsistent, unstable state. That shared design choice makes both tools incredibly reliable day to day.
Okay, so those similarities, the syntax, the repositories, the transactions, they make life easier. But now we need to dig into the differences, the things that really set them apart architecturally and for administration.
Right, and this is where you start to see the different philosophies, maybe the different histories showing through. The most fundamental split is obvious, of course.
The package formats.
Yep. APT manages .deb packages. Its backend, the tool actually doing the unpacking, is dpkg. That's the Debian Ubuntu Mint world. DNF manages .rpm packages, using the RPM tool as its backend. That's Fedora, RHEL, CentOS, SUSE. And these ecosystems are totally incompatible at the package level. You can't just install .deb with DNF or .rpm with APT.
Okay, basic incompatibility. Got it.
Yeah.
Beyond the file type, what's the first operational difference that usually trips people up when they switch?
I think it's the update workflow. How you get the latest package lists before upgrading. It's basically a two-step versus a one-step process.
Explain that. APT is the two-step.
Correct. With APT, you have to run apt update first. That command specifically goes out to the repositories and downloads the latest lists of available packages, the metadata. Only after you've done that can you run apt upgrade to actually download and install the new versions of your software.
So update the list, then upgrade the software. Two distinct commands.
Exactly. APT deliberately separates fetching the potentially slow network information from the actual installation process.
And DNF handles this differently.
Yeah, DNF tries to be a bit more automated. When you run a command like DNF upgrade or even DNF install, DNF will typically first check if its local metadata cache is out of date.
Automatically.
Usually, yes. It has a configured time limit on the cache. If the cache is deemed old, DNF automatically runs the equivalent of apt update before it proceeds with the upgrade or install you asked for.
So DNF often combines those into one command from the user's perspective.
Right, which simplifies the workflow, just one command to remember.
Yeah.
But sometimes it can make that DNF upgrade command feel a bit slower to start because it might be doing that metadata refresh first, whereas with APT, you might have already run apt updates separately.
Pros and cons either way, kind of. Convenience versus maybe more explicit control.
Pretty much. Now, that's a workflow difference, but let's talk about the feature that, for me, is the biggest administrative advantage of DNF, especially when things go wrong, like badly wrong after an update.
You're talking about transaction history and rollback?
Exactly. This is where DNF's more modern architecture really pays off for system administrators. DNF meticulously records every operation, every install, every upgrade, every removal as a numbered transaction.
And you can see this list.
Yep. It just run DNF history list. It shows you exactly what was done, when, and which packages were involved in each transaction.
Okay, a nice audit trail. But the real power?
The real power is DNF history undo. Let's say you run DNF upgrade, and it gets transaction ID 150. But immediately after, you realize a critical service on your server is broken because of that update.
Oh no, panic time.
Well, with DNF, maybe not full panic. You can just run DNF history undo 150. DNF looks at what transaction 150 did, calculates the exact opposite operation, and then proceeds to downgrade or remove all the packages involved to put your system back precisely to the state it was in before you ran that upgrade.
Wow, okay, that's huge. Like a system-level undo button for package operations.
It really is. It's an enterprise-grade safety net.
So wait a minute. If this is such a powerful, useful feature, why doesn't APT have something similar built in? Is it like a performance trade-off, or is it just harder to add to APT's design?
It seems to be mostly structural and philosophical. APT does keep logs. You can see what was installed. But its core design and dependency resolution are really focused on getting the system to the current desired state based on the available packages.
It doesn't track the how we got here in the same way.
Not in a way that makes clean rollbacks easy. DNF's architecture, partly thanks to how it uses libsolve and manages its data, was seemingly built with this kind of state tracking in mind, trying to replicate a DNF-style rollback manually in the APT world. It's incredibly complex.
How would you even do it?
You'd have to dig through logs, figure out exactly which packages changed version, manually find the older versions, hoping they're still available easily, and then force downgrade them one by one using dpkg or advanced APT commands, all while hoping you don't break other dependencies in the process. It's risky and time-consuming.
Compared to DNF history undo ID.
Yeah.
Yeah, night and day.
The lack of a simple, reliable, built-in rollback in APT is probably one of the biggest administrative differences. DNF just gives you much more control over the system's history.
That saved time, saved stress. That alone seems like a major win for DNF in critical environments.
Definitely. And being the newer tool, DNF also brought in some other advanced features, particularly relevant in the RHEL ecosystem, like modularity, or app streams, as they're often called.
Modularity.
Yeah.
Okay, how does that change things compared to a traditional repository where you just get one version of everything?
So traditionally, if a Linux distribution shipped, say, Python 3.6, that was usually the only officially supported Python 3 version you could easily install from the main repos. Maybe security updates, but you were stuck on 3.6 for the life of that OS version.
Right.
Modularity breaks that. It allows the OS vendor, like Red Hat, to officially provide and support multiple streams of key software at the same time. So within RHEL 8 or 9, you could have official streams for Python 3.6, Python 3.8, and Python 3.9, all managed by DNF.
And DNF handles keeping them separate.
Yes. You tell DNF which stream you want to enable for your system or even for specific applications. It manages installing the right versions and ensuring they don't conflict. It's huge for enterprises needing stability with older versions for some apps, while developing new things on much newer versions, all on the same OS install.
Okay, so that's built into DNF and the RHEL ecosystem. How does the Debian 2 world handle needing newer software versions not in the main OS release? That's where PPAs come in, right?
Exactly. Personal package archives, PPAs, that's the common solution. You find a third-party repository, often maintained by a developer or a community group, add it to your APT sources, and then you can install newer versions of software from there.
But that's different from modularity.
Very different. PPAs work, and they're widely used, but they come with trade-offs. You're trusting an external maintainer, not the main OS vendor. PPA packages can sometimes conflict with official packages, or they might break when you do a major OS upgrade if the PPA maintainer hasn't updated yet. Modularity is integrated, officially supported, and managed directly by the core package manager as part of the OS design.
So integration versus an add-on, basically.
That's a good way to put it.
Okay, so let's try and synthesize this for everyone listening. Both APT and DNF are incredibly successful. They solve dependency hell, they're stable, reliable.
Absolutely. And the day-to-day commands are remarkably similar, which is fantastic.
But underneath, there are clear differences. APT is mature, incredibly fast usually, and serves a truly vast ecosystem, highly optimized for getting packages installed.
Right. While DNF, being the newer rewrite, brought architectural improvements, it uses that superior libsolve solver, which really shines in complex cases. And it offers those powerful admin features, transaction history, the crucial rollback capability, and native support for things like modularity.
So it's not really about one being universally better, is it? It's more like they're each highly optimized for their own native environments and design goals.
I think that's fair. DNF definitely leans more towards providing fine-grained administrative control and features suited for enterprise stability needs, maybe.
And understanding these differences, especially the DNF history rollback part, is really critical if you're aiming for certifications, right? Like the RHCSA or maybe even the LFCS.
Oh, absolutely mandatory for RHCSA. You have to know how DNF history works and how to use it. It's a fundamental part of managing RHEL systems effectively. Understanding it for LFCS is also very valuable since you might encounter RPM-based systems there too.
Okay, so we've laid out the history, the similarities, the key differences. We hope that gives you a much clearer picture.
Now, we always like to leave you with something to chew on. A final thought.
Go for it.
Think about this in a real-world context. Imagine you manage a non-critical server, maybe a staging or Q-Day environment. You push out a routine update using DNF upgrade. But, it breaks something important. Maybe a test database connection just stops working.
Yep, happens.
How much actual cost in terms of system downtime, your own stressed-out engineering, time diagnosing and manually fixing it, how much of that is potentially wiped out by typing one single guaranteed command, DNF history undo ID?
Compared to the hours you might spend manually downgrading things in the APT world.
Exactly. The value of that command isn't just syntax, it's risk mitigation. It's potentially business continuity, even on a small scale, something to really ponder the next time you're about to hit enter on an upgrade.
A very powerful point. Well, that's our deep dive for today.
Thanks for joining us.
We'll catch you next time on The Deep Dive.